Hi students, and welcome to HSC Chemistry and the acidic environment video series. In this video we're going to look at conjugate pairs. Our Bronsted-Lowry definition actually allows us to start looking at not only how different types of substances behave when they're in solution and also when they're reacting with other substances, but they can actually start to give us an idea of the nature of different types of solutions, particularly of different types of salt solutions. In order for us to explore this in a little more detail, the first thing we need to do is to start to have a look at the idea of conjugates. Now, conjugate pairs are species involved in the transfer of protons. So we've said previously that our Bronsted-Lowry definitions are based on the transfer of protons. So one species being a proton donor, and that's equivalent to our acid, and one species being a proton acceptor, and that's our base. Now, of course, because this is a transfer reaction, that proton must go from one species to another. So our H plus is going to come from our acid to our base. But of course, as soon as that happens, what happens is that the acid is going to leave behind a base, that is, a substance that has lost a proton and hence has the capacity to accept one. And our base is turned into a conjugate acid, that is, a substance which was able to accept a proton and is now able to donate a proton. When we look at the idea of conjugate pairs, what we're looking at is a pair of acids and bases where we have an acid and a conjugate base representing one pair, conjugate base, that represents one conjugate pair, and then the base and the conjugate acid represents the second pair. And we'll look at some examples so that hopefully that will make a little more sense to you in a moment. The equilibrium position of an acid-base system is determined by the relative strengths of the bases involved. So if we look at the bases, then that gives us a bit of an idea about where the equilibrium lies, either to the right, favouring our products in this case, or to the left, favouring the reactants. If the equilibrium lies to the right, the conjugate will be weak. That is to say, hydrochloric acid, when we dissolve it in water, will form H3O plus and Cl minus. In this case, we know that hydrochloric acid is a strong acid, and therefore the species that is left behind after the proton moves across to the other one is what's called the conjugate base. In this case, it's the chloride ion that's left behind, and it will be correspondingly weak as a consequence of the fact that the acid is strong. Strong bases, likewise, have weak conjugate acids, and this is one of the things that we look at when we're looking at our conjugate pairs. Likewise, if the equilibrium lies to the left, the conjugate will be strong. So where we have something like, we've also looked at, say, acetic acid, and when that combines with water, it will form the acetate ion, C3COO minus, and the hydronium ion again. In this case, we have our acid and our conjugate base. And because this one is a weak acid, its conjugate will be strong. I've used acids with both of these examples, but of course they likewise work with bases, and we'll have a look at examples of each of these in this video. Weak acids have strong conjugate bases. So the strength of an acid, we've said before, is a measure of the degree of ionization. And as a consequence of that, HCl is a strong acid. What this means is that this chloride ion is a weak base. In this case, the conjugate of the HCl acid. On the other hand, acetic acid is a weak acid, and as a consequence, its conjugate base is strong, is a strong base. The general formula then is the acid goes to the H plus ion, which it's going to donate, and what is left, the anion that's left, is called the conjugate base. So this would be the conjugate pair. The acid and its conjugate base form the conjugate pair. Bases work the same way as acids. The strength of the base is a measure of its ionization. But more importantly, its ability to accept a proton. Because we've changed our definition now, this is what becomes critically important. The strength of a base is related to its ability to accept a proton. Sodium hydroxide is a strong base because the OH minus ion will accept a proton and form water. This is a strong base, and water is a considerably weak conjugate acid. Ammonia, on the other hand, is a weak base, and that's because when ammonia accepts a proton, it forms the ammonium ion, which is a strong acid. That's the conjugate of the weak ammonia base. In this case, the base accepts a proton and forms the conjugate acid. So what we might have to do sometimes is look at conjugate pairs, identify the acid and the conjugate base and the base and the conjugate acid. Stop the video if you want to have a go, but I'll go through it now for you. What we can see is that there is an H plus ion that's going to be transferred. Now, obviously, it can't be transferred this way because there is no hydrogen here. So therefore, it must be transferred this way. That means the water is actually acting as the acid and the OCl minus ion as the base. The base has accepted a proton, so this is the conjugate acid, and the water has donated a proton, so the OH minus is the conjugate base. How did you go? Thanks for watching.